The next presentation is Moon Sighting Satellite, Otsukimi, by Ms. Hala Osman Al-Mubarak from Kyushu Institute of Technology. So please start.
So good morning, everyone. I'm Hala from Kyushu Institute of Technology. I'll be presenting on behalf of my team the moon sighting satellite Otsukimi. Okay. So first of all, the idea. Our idea is not only focusing on the scientific gain we have, but also on making change on people's daily life. So actually, we are targeting one of the biggest communities in the world. We are targeting the Muslims community, which is 23% of the world's population. Those people use the lunar calendar. And our mission is that we want to capture an image for the lunar phases from the Earth, as it's seen from the Earth, but we use it from, we capture it from space. So Muslims countries depend on the lunar calendar on performing all of their religious rituals, their celebration days, and many cultural activities. So as introduction, we want to know a little bit more about the lunar calendar. So as we see, the lunar calendar have 12 months, almost like the Julian calendar, and it's directly, each month is indicated by the phases of the moon. So it begins with the new moon and ends with the new moon again. The Julian calendar, actually, it's 11 days more than our calendar. And in our calendar, there is two types of days. That's because according to the motion of the moon and Earth and around the sun, it's 29.5 days. We don't have a half day. So it's either 29 days or 30 days. And actually, we need to know the difference between both of them. It's like when it will be a 29 day and when it will be a 30 days. So this is indicated, as we see, by the beginning of the month. For example, in the end of the month here, we see that we are going to the new moon phase. And in the new months, if we have seen the crescent, this small silver crescent in the beginning of the month, it means that we started from this day, counting, this is the first day of the month. But if we pass the 29th day without seeing it, so we complete 30 days, and after that we go to the new month. So for more understanding, as we see in this picture, we have in the first part of this picture how the alignment of the Earth, Moon, and Sun. And in the down part, we can see how we see this moon, how we see the phase from Earth. So in each end of month, people sight the moon. They go out in the clear sky, they try to see the crescent in this phase. And as we see here, in the new moon phase, the Earth, the Moon, and the Sun, they are aligned all in one line. So basically, we cannot see the moon. We cannot see it because we already see the Sun. It's in the same line with the Sun. But after that few minutes, we can see the moon. We can see the crescent born in this moment. But after a few minutes, again, this moon set. So again, we cannot see it after the sunset. So actually, it's a critical time that we want to sight the moon in this specific time from the 29th day. This is how it looks like. We have the time, which is people go outside to the clear sky, try to see the moon. They look it on the west side of the sky. And it should be before the sunset, where they can actually see it, maybe sometimes by just the eye. And happens in the 29th day. But the moon actually stays there for a few minutes. And after that, it goes, sets down, and we cannot see it anymore in our sky. So in this picture, actually, fortunately, this is a clear sky, so we can see the moon. Our problem that we are wanting to solve is that in this community, they need this calendar, but they cannot judge the new moon if it's appeared or not in the 29th day, because nowadays we have the air pollution problem, we have the light reflection from the horizon. Also, many times we have the bad weather in these areas, and it's kind of sometimes difficult, very difficult to sight the moon if it's not really impossible at that short time. So we are proposing our solution. And our solution is reflecting directly to these people, because all the rituals and celebrations and festivals depend on this lunar calendar. So what would happen if we didn't solve this problem? Some people in some areas will sight the moon, while the others cannot see it. So some of these people will start the new month, while the others don't. And this is lead us to a non-synchronized calendar through all these countries. So there is, from beginning, so there is some conditions that Muslims use to sight the moon. They don't realize on the calculation-based methods, because they confirm the sighting the moon by the calculations, but they need to judge by the sighting itself. So the conditions are that the conjunction has to be occurred before the sunset. This is how we know that we are in the 29th day, and we started to sight the new crescent. The second one is that we need to see it, like this is a possibility of seeing it in one of the areas in a region that's sharing the same night. Additional conditions added by the astronomers is that the moon sets after the sunset, where there is a possibility of sighting. Also that the angle between the crescent and the horizon at the sunset time, it should be at least 5 degrees, and the distance between the sun and the moon is at least 8 degrees. So for us, it was a little bit of a problem how to design a satellite. What would solve this problem, because it's, we need to design a satellite that could capture the moon in this specific time. So now we will present about our solution, and the contents are the mission objectives, the concept of operation, the key performance, and implementation plan, and finally conclusion. So our mission statement is that we want to capture images for the moon phases at the sunset time and distribute this data to users within approximately 2 hours. Secondary missions would be observing the moon at all times. It would be fascinating to have some picture in the eclipse time. Also, we want to establish a satellite ground station operating from several countries, and an online database for all these data and images. And our system would be a very good example for developing countries to solve their problems using the space technology. Also, we will encourage the universities to develop nanosatellites based on other successful missions in international work. Our satellite is a 30 kilogram mass with this 50 centimeter cube size. And as we see, this is the internal panels, including the subsystem for like power and OPC, and the outsider, including the sensors. So the concept of operation, as we said earlier, we wanted to design a satellite that could really capture this image at that specific time. So after a lot of thinking, we found that this orbit, the dawn-dusk orbit in the sun synchronous, could do it, because we can set the local time, especially over the area that concentrated with Muslims. It's North Africa and Middle East area. So we can use this dawn-dusk orbit. So we could say that our satellite at that time would be there to capture this image for the newborn crescent. And we calculated the inclination to be 99.5, so it would have multi-passes around this area, and with attitude of 1,000 kilometers. We will use 3-axis attitude control determination, and for the image sensor, we will use special filtered lenses, because we don't want the sun to distract this image. The concept of operation for our ground segment, the downlink of the images would be in each orbital period. We have multiple passes at sunset over the Middle East area, and also we have selected a near North Pole ground station that provide us with each orbit we can communicate with our satellite. For a visibility window for communication of about 10 minutes, and we could downlink around 20 images per pass. We designed our structure of the satellite according to the H2A rocket, and we have 2 modes of operation. The normal mode is when the satellite is regularly taking pictures for the moon phases. and the mission mode, which is taking multi-images at specific time, activating the satellite from the ground station. Our key performance is that the camera, which is high resolution camera, and also the AODS, the attitude control system, precisely will track the moon. Also, the communication system, which have a reasonable high data rate to downlink this data. So this are some calculations for the size of the image we need and the resolution we need, and also the attitude control system using a 3-gyro axis stabilization system, and the communication, which consists of VHF-UHF transceiver for downlink and command, and the S-band with high rate with 2 megabit per second for the mission data. So our expected product is something like this. We need a photo from space for the crescent at this time of the month to indicate the new beginning of the new month. This image was photographed from the ISS. So our implementation plan is that we have product and services. The product will be the moon sighting satellite, the services that the ground station network, database for the moon images, and we will increase the outer space knowledge, and we will provide a community need, which is the lunar calendar, with a lifetime of 2 years. This is the total cost of 6.5, with much of it 4 million for the launch. And the responsible organization, we propose UTEC and other interested parties for this. This is detailed implementation plan from the concept design up to building the satellite, testing, verification, and validation, and launch. And as a conclusion, our mission actually provides opportunities for space science and satellite technology for developing countries. And our mission is, it would be the first space mission dedicated to moon observation from space as it's seen from Earth for cultural purposes. And we will solve regional problems by international efforts. This is a good example. And this mission will provide an online database for all the people who are interested in moon observation. Our expected partners and investors are basically, this is some examples of them, like in Egypt from UAE Space Agency, and Saudi Arabia, and so on. So thank you very much for this opportunity. Thank you for attention.
Thank you very much, Ms. Al-Mubarak. So the question is, we have already announced, the question is limited to just reviewers. So please ask.
I've got a question about your power budget. You say the average power is 40 watts, but you have body-mounted solar panels and 50 by 50 by 50 centimeter box. How are you going to get 40 watts average power?
Okay, we are targeting to use very high efficient solar panels. Of course, the area will not be sufficient, but the reason we are that normally the satellite will be oriented to the moon, and so the operating time will be very short, and the other period of the orbit we are targeting to have some orientation toward the sun to achieve much power as much as we can. But normally, maybe sometimes we will not work every day, so the loading will be much for the battery, and the rest of non-operating time will be for charging the battery itself, and we are not always working, so the 40 watt is the maximum or the peak power expected to be drawn from the system. But this is not the average value.
It says average power in your table.
Or maybe it's a mistake, but...
I'm also not sure why you need such an accurate attitude control system, because the moon is quarter of a degree. It's a fairly large target, and I mean, if you point within 0.1 degrees towards the moon, it should be more than accurate enough.
Okay, actually, we are using a COTS component, so we are searching the database for available systems. We found such. Maybe this is higher accuracy, okay, but we achieve our target.
Thank you very much. Your satellite has a very high altitude, 1,000 kilometers.
Yes.
How do you think about the parallax of the between satellite position and Earth surface?
Okay, we select 1,000 kilometers because we are not targeting remote sensing or Earth observation. So we try to go as much as closer to the moon. Anyway, the moon is very far. It will not matter this 200 meters difference.
Yeah, my question is that the difference of the shape from the surface view and the satellite from the satellite view.
So the ratio between these two distances, we expected that the change is not very high. So the distance of the moon and in respect to the Earth.
Okay, the 1,000-kilometer worries me from space debris. That you need to get out of the way in 25 years. I don't know if you can do it from 1,000 kilometers. So that's a problem. The other question I have for you, and it goes back to the attitude determination and control requirements, and maybe the answer is the same. I agree that you have a really nice pointing system. I don't know if you need it. The same question goes with the 30 kilograms. Do you need a 30-kilogram spacecraft to do the mission, or can you do it with a smaller CubeSat class system that costs a lot less? And maybe what I'm asking is, do you need the quality images that such a large spacecraft provides, or could you do it with a smaller satellite?
Actually, we put our margin because we are going for this competition like nano satellite scale. We actually don't target only this is main mission. We may have another experimental or secondary missions, so we put this margin. This is not only the main mission. We can achieve this main mission by a smaller one, of course. But as we expecting, maybe we have some margin in mass and volume, and of course the power we need. Maybe we need this volume at least. So this margin of mass and volume can be used for another experimental mission. This is another objective we are targeting to do.
Just so you know, that the argument you're making for this mission, you can have a primary mission. You don't need to have other missions on board.
So I think also for this question, we trying to use, for example, the camera system, the opticals. It's a little bit tricky. So we targeted a COTS, but we cannot say exactly we will use this kind of camera, so we cannot say this size. And also the power. One of the biggest thing that, yes, we need this area of the satellite for the power, but maybe it will be less than 30 kilogram. And if for CubeSats, it's really interesting. And maybe we need to focus on the camera and the CubeSat and the power only.
Okay, so I'm interested in the optical system of your satellite, and maybe the resolution of the image will decide the focal length, and how you can decide the aperture of the camera, because in order to have a very good signal-to-noise ratio, aperture should be very large. And so, what is your requirement, and how you can decide the aperture of your system?
So this is started by trying to select the resolution, and the resolution is constrained by the downlink size, data size we have. So one of the things that we don't want a very high resolution image because it will increase the size for the data. It will be a problem in downlinking, and in the same time, we want an image with some resolution. Even the proposed resolution here is a little bit higher than just to see the crescent and judge there is a crescent. So according to that, we made some calculations and we proposed this ratio. And according to this calculation, we have a good resolution for the image we're expecting.
So this is only the resolution. And the resolution will decide, focal length as well as the pixel size, pixel number.
Pixel numbers.
But I want to know, the signal to noise ratio, how the bright the image should be. So there is no consideration about that in your papers.
Yes, maybe because some of the calculations were done and then they wrote just the final result they want from our team.
Okay, thank you very much.
Thank you.
Presentation. So,